Morning, everyone. So we're going to continue on learning about the momentum concept we introduced yesterday. We started looking at the two main setups already. Basically, momentum is conserved during a collision when there's a hit or when there's a collision, when there's two objects smash into each other, or a conservation problem where we had the space shuttle question. We start off with one object, it may break off into many parts, but somehow even through that explosion and through that separation, momentum is a concept that has to be conserved. So throughout this chapter here, believe it or not, the physics is all just the same. It basically says here, because of momentum conservation, we can easily say here, the momentum in the initial diagram, I can even use that sigma notation, all the momentum at the beginning has to equal, it can't be lost, and equals all the momentum at the end. Today we're going to have a look at collisions in a little more detail, get some practice problems in as well. As we finish off with one-dimensional collisions, we're going to do something called inelastic and elastic tomorrow, working our way towards two-dimensional momenta. It'll be harder because we need to do components again, but we've already done all that vector addition stuff from the first chapter. Just before we get into a few questions here, our next chapter we're going to spend talking about energy in general. One specific type of energy is called kinetic energy. I'm just going to introduce to you the formula here because it also shows up in this chapter. That way we get a head start later on, as well we can study these momentum concepts in a little more detail as well. So just before we look at a collision here, one form of energy is also a conserved quantity. We'll talk about En should equal to E out. Okay. But in this case here, I just want to introduce to you the first type of energy, which is called the kinetic energy. Probably have heard of this before. You can say Ke for this. Sometimes they say E subscript with the K here. Doesn't really matter what your placeholder is. Just make sure you know that this is kinetic energy. And you may remember from your earlier science classes, kinetic energy is the energy for your kinetic or your energy for your motion. So in this case here, kinetic energy is the energy of motion. Like we'll see in the energy chapter, the SI unit for energy is the joule. Many times we use kilojoules, so thousands of joules as well, depending on the magnitude that we have, but pretty much objects that are in motion have this energy. Objects that move quicker will have more kinetic energy, slower that has less kinetic energy. If you remember, let's say in your chemistry classes, if you heat up the temperature on a sample, the particles tend to move faster, they vibrate more, they speed around a little bit more. As they tend to move quicker, their average kinetic energy goes up, and then when we stick a thermometer in which measures kinetic energy, that average energy has gone up and the temperature has heated up. So for kinetic energy, the formula we're going to be working with here is the kinetic energy, let's call it Ek. It's also going to be related to those two same concepts as yesterday, which is mass and velocity, but a slight alteration of the formula here. The Ek has a constant scaling factor of half. It is going to depend on your mass. So if I have a small object that's moving versus a big object that's moving, if they moved at the same speed, the bigger object has more kinetic energy. It takes more energy to move a bigger object, or as it goes, it has more energy. And similar to yesterday, it's going to be m times the v, or the velocity. The velocity here is the speed. If you manage to get a really hot, heavy object moving really quickly, that's going to have a lot more energy than if it were moving slowly. Kinetic energy, this is actually the first time we actually get a little bit of a relief here. Most of the concepts, displacement, velocity, acceleration forces, all those type of vectors, we're going to find mainly in the next chapter, energy is actually a scalar. So if you remember from your definition, scalars only have magnitude. Scalars only have a number to it. There's no more sense in talking forwards or backwards or adding negatives to numbers to indicate direction or anything like that. One way to tackle that, earlier we knew velocity was a vector. How is it possible energy ends up as a scalar? What we're going to do, whether the velocity ends up being positive or negative, we're actually going to take the velocity and square it. So if I took a positive number and square it, it's positive. If it was in the opposite direction, it's a negative number. Also square it, it becomes a positive number. That gets rid of the problem of arrow. As we're going to see in the next chapter, energy can still be positive or negative, but in that case there, we're actually talking about energy, either gains or losses from the system or the surroundings, less so direction. So because energy is a scalar, you're going to find this is a lot easier in the next chapter. You just basically calculate the kinetic energy of each part individually, and you can just simply add them. There's no components, there's no breaking up thetas, there's no x and y components or anything like that. So hopefully you find this formula a little bit easier, because it does relate to those very same formulas like like m and v, which momentum also does. There's one other way you can word this here, derive it for you shortly here. The kinetic energy is also going to be p squared over 2m. We're not going to use this latter formulation too much, but if you go on to physics, you will see this. Let's just punch our way through the math here. The p, or the rho, which is momentum, we take the square of that. So the top of it will be mv all squared divided by 2m. When you square a bracket like this one here, the square just distributes in. So we have m squared v squared over 2m. And if you work out the math here, the m divides the first m squared there. We have a constant of half, and there we get our half mv squared, and we get back our formula half mv squared. So on your formula sheet here, it'll be quoted for you. The EK is half mv squared. As we do some more problems with collisions, because we'll have masses and we'll have speeds, we can actually calculate what's the kinetic energy of these particles. Did the energy change actually before and after? So let's have a look at a few collisions here. I'm going to keep my numbers fairly simple. Hopefully it'll help you out as we learn this. I'm going to write the first one out here in words here. A 1 kilogram, I'm still going to call it a car and a truck just so that you get some familiarity. It could be any object description. So a 1 kilogram car moving at 5 meters per second. That's a positive number, so you can imply that's going forwards. This one here is going to hit a 2 kilogram truck. This truck here, it could be moving. We'll do that in a later question, but just for simplicity, let's just put it at rest as well. It's a 2 kilogram truck at rest. It wasn't moving. It had no momentum to begin with. What I'm going to give you in this picture here is, depending on how the collision ends up, remember from yesterday, we need to be told a little bit of what's happening afterwards before we can apply a conservation of momentum question. So let me just draw a quick picture for this. The beginning setup, let's call this situation 8. The beginning setup here is a 1 kilogram car. You've checked the SI unit. This is 5 meters per second, which is positive, which is perfect. This is going forwards. It hits the truck again, rear ends it. Okay. 2 kilogram object at rest. This was not moving. That's going to be a constant before picture. The question here is, what can happen afterwards? What could possibly outcome after these two objects hit each other? So I'm going to give you a few different setups. I need to be told a little bit more. I can't just predict from scratch. In this case here, one possibility is when this car is speeding along and hitting this 2 kilogram mass, maybe after the collision, the first mass completely comes to a stop. So maybe the 1 kilogram object ends up stopping, and because this one ends up stopping, the 2 kilogram object starts sliding off at some velocity. So we have first object moving, it hits a steady moving car, the first object comes to a direct halt, it just stops, and then we're going to see what's the final speed that this latter object has. So in that setup, let's say this is situation 8. Our physics is simple. It just says P in equals to P out. Momentum, as this motion product is a conserved quantity, it has to stay the same before the collision and after the collision. We're going to write a P term for every single object that we have. So again, just for clarity here, I can say P of the car plus P of the truck has to equal to P of the car after, let's say final, plus P of the car, P of the truck final. You'll probably, with more practice, you'll probably be able to skip that step there, because we also know our formula, momentum is equal to mass times velocity as well. We can actually right away put m times v and m times v for these formulas. So what I would do here is I would say, well, I have two objects at the beginning. I'm going to go m1 v1 plus m2 v2, where object 1 is the car, object 2 is the truck. And on the other side here, we have m1 v1 final plus m2 v2 final, because who knows, after the collision, their speeds might be different, but at the very least, the momentum has to be conserved, the momentum has to be equal. So let's just punch our way through these values here. I have a 1 kilogram object moving at 5. My 2 kilogram truck here is not moving, so it has 0 velocity. This has to equal to assuming again the whole car is intact, so it's still 1 kilogram. It's a very light car. We have 1 kilogram. It actually travels at no velocity, so 0. And the question here is, how much faster does the truck end up moving? Again, I'll show you a 1 middle step here. 1 times 5 is 5. At first, the car had a tendency to stay in motion 5 kilograms per second. The truck wasn't moving, so it contributes no momentum. The total momentum coming into this collision is 5. Afterwards, even though momentum could have been transferred from first object to second object, the total momentum still has to be 5. So in this setup, if the car comes to an immediate halt, the first object has no more tendency to stay in motion. What does the truck have to leave with so that it conserves the momentum of 5, so that it keeps this tendency to stay in motion going forwards? So hopefully that's a fairly easy problem here. There's a bunch of zeros. We have 5 is equal to 2 times v2f. So v2f, the final velocity of object 2, which is the truck, is 5 over 2, which is 2.5. Again, make sure you have units. So this is a velocity, so meter per second. And also don't leave things in fractions, or else it looks like it's an infinitely precise number. So based on this work here, at first we didn't know the speed to begin with, but now we know this truck has to move off at 2.5 meters per second. If you're comparing the numbers here, it shouldn't be all that surprising to you. We had a lighter object traveling quicker. It had a total tendency of 5 to stay in motion. When this object comes to a stop, halt, right after the collision, because the truck happens to be twice as big, when that 5 tendency to stay in motion is transferred to 2 kilograms, the heavier object doesn't need to move as quickly, and it already has conserved the 5 tendency to stay in motion. Because I introduced to you the kinetic energy formula as well, now that we have all these formulas here, let's not say the energy is equal for the time being. We're going to do that in tomorrow's lesson, but let's calculate. What is, just for comparison's sake here, what's the kinetic energy of this car plus the kinetic energy of the truck before the collision? And let's compare it to what's the kinetic energy of the car after, or final, plus the kinetic energy of the truck after. Again, we sort of know conservation energy, but in this case here, we're going to see that the energy is actually not conserved. So something strange happens. Let's just play around with the formulas. Kinetic energy, I just gave you the formula, is 1/2 mv squared. So what we're going to do, I'm just going to punch our way through. With our 1/2 mv squared for the car, 1/2, the mass was 1, the speed was 5 squared. That's the kinetic energy of the car. Let's add that to 1/2, the truck was twice as heavy. This one here wasn't moving, because kinetic energy is moving energy. No surprise, that one there just drops up to 0. On the other side, the car afterwards, 1/2 mv squared, 1.0, the car came to a halt, so it's 0. And then we're going to have 1/2 mv squared, 2.0 times our velocity. At first we didn't know what it was, but based on conservation of momentum, the truck has to leave with 2.5, and that'll actually go to kinetic energy. So let's just punch our way through the values here. 0.5 times 5 squared. The car at first has 12.5 joules of moving energy. The truck wasn't moving, so that contributes nothing. On the other side here, the car ends up not moving, so 0 joules. For the truck here, 0.5 times 2 times 2.5 squared gives me 6.25. Just a general comparison with the energy before and the energy afterwards, we'll notice that the initial energy was actually higher. Initial moving energy, kinetic energy was 12.5. You'll notice afterwards when the car stops and the truck ends up moving off at 2.5, the overall energy that's still moving energy is actually less. Can you think of a reason why this may be? I thought energy is supposed to be conserved. It's supposed to be 12.5 on this side, 12.5 on the other side. Again, we're going to flesh this out a lot more in the next chapter, but basically, this is just tracking the kinetic energy form. This is just tracking the moving energy type of energy. When you have a car crash, I would imagine there would be a loud bang. Okay? Some of the energy is lost as sound. I would imagine that surfaces, as they rub against each other, they're going to produce a lot of friction, and some energy is lost to heat. So energy can actually convert between different forms. Just for thinking's sake here, we're going to say something like E total, in this case here it started off as kinetic energy, E total will be split between, sure, the EK final was only 6.25, but maybe some energy is lost to sound energy, maybe some energy is lost to heat energy and other types. So far at least the Energy, yes, we should have 12.5, yes, it should be conserved, but at least the moving energy form of it is actually less because some extra energy was lost due to these other transformations, these other types. So, just one other sort of side calculation you can do for the problem. That's setup number 1. So we had our collision, the first object came straight to a halt. What if we do setup number B? I'm going to keep all the starting conditions the same, so we have some familiarity. 1 kilogram going at 5 meters per second, it was forwards. 2 kilogram truck, but this one here was at rest. So that was the before picture. This time I'm told, instead of the first object coming to an immediate halt, what's going to happen here is they're going to end up sticking together. We're going to see tomorrow's lesson, this is going to be referred to as an inelastic collision. Because it's inelastic, basically the car and the truck gets mangled together, they travel off as one combined mass, and we're going to have a look at what the formula looks like at that point. So what if I'm told, unfortunately this time the 1 kilogram and the 2 kilogram object, they just get mangled together. It doesn't have to be as simple as shown in this picture where the car is perfectly neatly behind the truck. The metal could really get interwarped and mangled together, but in total what we care is we're now on total mass of 3, assuming no bits or pieces fly off this collision. So we have to be given that information. The before is still the same as earlier, but we are actually ending up here with an after case. Again, based on the numbers that I've given you here, we just don't know what the final velocity is going to be. Just sort of going into this, we realize that this mass here is actually heavier, so we would imagine that total speed would be less, but it may even be less than the 2.5 we had calculated from earlier, because this was just a truck moving, and in this case here, we're actually car and truck together. So again, the physics is simple. The physics says Pn equals to Pout. All momentum has to be conserved for every collision. Unlike energy that can change forms and be passed between surroundings and systems, the momentum, this motion product number, total, has to stay the same. So just like before, I can say P1, P2. If I were doing this now, I would just go, well, at first I have two objects, M1, V1 plus M2, V2. I'm going to add up those momentum because they add linearly, so there's no squares or anything involved. Those are the total momentums at the beginning. And at the end, this time, because I only have one object, sure, you could call this M3, M3 moving at V3 or whatever, but I know M3 is actually a combination between M1 and M2. So I do have one object only, so it's just going to be one of these M times V terms, but I can be a little bit clever here and I can say this is going to be M1 plus M2. Super important if instead of giving you the actual numbers for masses, maybe I put an M for one of these masses. Because you formulated it this way, it's the total mass between objects, you can carry an M through the rest of the problem and see when you can solve for M later on. In this case here, no problem, because I have the 1 and the 2, it's just going to end up being 3. But similarly, we don't know what the final velocity is. Sort of intuitively looking at this picture, because I had some tendency to go in motion to the right, even after I smushed together, I would expect this to go to the right. To conserve a tendency, to conserve a momentum to the right, I would imagine that simply continues forwards. Remember, momentum is a vector in the direction of velocity, so I have a 1 kilogram object traveling at 5, the 2 kilogram truck here, twice as heavy, it was at rest, so it contributes no momentum. And the problem that we're going to do later on, maybe this will have speed, maybe it'll have a backward velocity or forward velocity, you just punch this turn in here, and that would contribute to the total amount of momentum that will get conserved. In this case, you're still very simple. This momentum has to be equal to the combined mass, so 1 plus 2 is going to be 3 kilogram mass total and the velocity. We just need one single M times V term for any object that I have, two objects at the beginning, one object at the end. So just like earlier, we have a 5 tending to stay in motion. The second object here is going to be a 0. This is equal to 3 times the term of velocity. For momentum to be conserved, for this physics in our universe to be obeyed, 5 divided by 3, 1.67, I think it is, 3, so let's just say 1.7. So again, the physics is the same. We had 5 momentum from the car, the truck didn't contribute any momentum. For that 5 to be conserved in this after picture, this second object, the combined mass of 3 kilograms, has to zip off at 1.7 to conserve that 5. And if you compare this picture to the one that we just did, again, it's a heavier mass, it even travels 1.7, is even slower than the 2.5 we had calculated for just the 2 kilogram pulling off. So, Again, because we have the kinetic energy formula, let's just compare. How do the energies look like in this problem? So if I, just as a follow-up here, if I did a half mv squared, half times massive 1, 5 squared, plus half, I know the second object here it's not moving, normally does it have no tendency to stay in motion. This one here is the momentum, this one here is the energy, sort of argument. We're going to have half times m, the kinetic energy would also be 0. Again, in total it should be equal, but let's just compare the moving energy. At the end I only have one object, so half times a 3 kilogram object. I just calculated this one here being 1.7, so because here it's 1.7, can we go 1.7 squared? So let's just figure out here, I'm going to have 25 times 1 times 5 squared. Starting energy was the same 12.5 as earlier. This one here had no joules. 0.5 times 3 times 1.7 squared gives me 4.3. So in a similar situation, the moving energy I start off with is 12.5. The amount of energy that's remaining for motion energy is 4.34. That means some of the other energy was lost to maybe even light, sparks that come from the collision, sound, heat, and one last sort of setup that can happen here. We've watched these two objects. We're going to still take the same before numbers. We watched the two objects. One came to an immediate halt. One of them actually came stuck together. This tomorrow will be called an inelastic collision. Probably the one that you're expecting is when two objects collide with each other, there's probably a little bit of a bounce back. There's probably a little bit of a rebounding feature. So let's just finish off with this question here. We'll start off 1 kilogram object. I'm keeping the numbers the same so we can compare easier. So 1 kilogram object hits a 2 kilogram truck that's at rest. The before hasn't changed at all. But this time what I'm going to tell you, I need to give you some information for the after. This time we're going to see that the objects end up, as they collide, they bounce off each other. And because these are variables in the same formula, I don't always need to be asking you for this velocity. Let's say I actually give you the second velocity. You can actually calculate what the initial velocity is supposed to be. So let's say in this setup here, there's the before, here's the after. This time the car and the truck don't get mangled together. So I'm just told, okay, what's the car's velocity afterwards, the v1f, if I'm told that the truck moves after at, just going to make up a number here, let's make it 6 meters. It's actually quite fast, right? Because it was only 5 meters per second to begin with. Let's just see what the math ends up being. So, physics is easy. Pn is equal to P out. Momentum conservation. In this case here, because we're one-dimensional collisions, objects can only go forwards or backwards. The collisions are fairly boring. When we do a two-dimensional collision, the physics will still be the same. Pn equal to P out, but there's going to be a lot of components that we need to deal with before. Let's have a look at our formulas again. I'm going to write an MV term for every single object that we have. So M1V1 plus M2V2. 1 is the car and 2 is the truck. The physics says this has to equal. I still have two objects at the end, M1V1F plus M2V2F. And I'm just going to plug away through the numbers here. M1 was a 1, the speed was 5, plus M2, which is 2, with a speed of 0. So 0 there. This has to equal to my car, 1.0. This time, oh, the unknown is V1F, so be it. I wasn't told it came to a stop, I wasn't told it smushed together, but I'm looking for the V1F if I know that the truck 2.0 moves off at 6. So it's the same physics, the momentum has to be conserved. We still have a tendency to stay in motion of 5. This one here contributes nothing, so 5 plus 0. We have a total tendency to stay in motion of 5. If I calculate the tendency of motion, whoa, this truck here actually left 2 times 6 is 12. This one left with a tendency of motion. What speed does this car need to rebound backwards at so that the total overall conserves the 5 that I brought in? So let's just work our way through the math here. I get 5 has to equal to V1F plus 12. And if I do a subtraction, V1F is going to be negative 7. Remember to have units. Remember to write your answers to 2 or 3 basics in physics. And we have our speed, V1F. The final velocity of the car is actually negative. What does this negative mean? So backwards, you're correct here. Velocity is the vector, so because they're rebounding off each other, they've collided at this point here. As the truck moves off quite quickly, this one here is 0 seconds. So somewhat unrealistic in terms of the numbers because the truck is actually ending up moving faster than even the car can when the truck is really heavier, but based on the physics, that's what we would expect. We would still quote the final velocity of the car as negative, because negative refers to the backwards direction. In case your question already has objects moving backwards, when I was punching in the formula for V, maybe I need to put it in at a negative 7 right away. Sometimes a negative, like in this question, comes up from calculation. That is just studying some more collisions, keep practicing your way through the worksheet. I wanted to show you the collisions don't just have to be between two objects. I'm going to leave you off with this question here. What if I have a really fancy collision? The thing about this here is I'm going to do P in equals P out. The only thing I need to be careful of is the collision all happens at once. So I'm going to leave you for this question here into a sketchy picture with different numbers. Let's say I have a 200 kilogram whatever car, bike, what have you. This one here is traveling at 14 meters per second. If it was kilometers per hour, I would need to divide by 2.6, but this one here is already in the correct SI unit. This one here is going to sort of catch up to a second object. Second object, I'm still going to make it, let's say, twice as heavy, just for convenience, so 400 kilograms. I'm not going to give you the initial velocity of that second car. And then finally, unfortunately, this is a really bad collision, we're going to end up colliding with an 800 kilogram. These masses could very well have been any number, you just punch in your respective ends, and this one here will always be up. Well, I mean, so, in the question that we're studying, kept at rest. The collision could have even be this one's moving backwards, or it could have been different. So, let's set up. We know, sort of based on this picture here, the V2 should be less than 14, so that way this first object, when we call this object, let's say mass 1, mass 2, mass 3, that way the mass 1 can actually collide with mass 2. Just to keep things simple here, so that we can go P in equals P out, let's imagine by the time the M1 catches up to M2, the M2 has just hit M3. So all three collisions happen all at once, and we want to see what happens after the collision. Say the 200 and the 400 kilogram end up squishing together, so 200 and the 400, again that mass there may be mangled out together. I'm going to tell you that this one here ends up traveling this way at 2 meters per second. The question here is the 800 kilogram object that was sitting at rest. I want to know what its final velocity is. So leave that question for you to try out there. I'll give you a quick hint just how you're going to set up this problem. Every time you have an object, you're going to put an m times v term. So I would expect to see something like m1 v1 plus m2 v2 plus m3 v3. Those are for the three objects. The question or the unknown here is the v2, so this is going to stay as your variable. I need to make sure I have all the other numbers. Actually, I'm not there, I'm going to give you this last number. So let's make this velocity, let's say it leaves with 8 meters per second. So sorry, I needed to give you that in the question. Afterwards, we end up having two particles. You could rename it. You can say M4, V4, M5, V5. But again, just like we did in the last question, we saw that M4 is actually a combination of M1 and M2. So for the first object, I might say M1 plus M2 times the immediate velocity, and then we have our M3, plus M3. So every time I have a single object, I would expect to have an m times v term. The physics part of it, believe it or not, is just once you find out the tendency to stay in motion, all that has to be conserved, all that has to equal what it is after. One extra caution as you practice your way through here is because this 2 is pointing in the backward direction, when you actually punch in the 2 here, this should be punching as a negative 2 meters per second. So make sure you add that negative 2, you can work your way through the math there, and see if you can find how quick is this middle mass moving before this all collision. That's it for one-dimensional collisions. Tomorrow we're going to come back and we're going to study more of this inelastic collision stuff. What if objects stick together versus the opposite, what's called an elastic collision. The math gets a little more challenging, but we're doing it. Thanks guys, take care.